Today I'm going to talk about solitons and their interactions. This is mainly based on two papers that we did with my PhD student, João. Okay, first I will introduce the concept of soliton and give some historical context, and then I will try to show it more rigorously, mathematically. Then I will talk about solitons in 1+1 dimensions, and then higher dimension, I give some examples, but the main focus of this work is in 1+1 dimensions. Then I will talk about the kink-anti-kink collision in two different contexts. One of them about normal and quasi-normal modes in kink excitations and kink-anti-kink collisions. And the second part, I will talk about the kinks that they are highly interactive. They are called long-range kinks. And there were many works actually in this line that since last year, people understood that what people were doing was actually wrong. The way you do the collision really matters. It can't be like the normal kink. Then I will explain it better. Then I will just give some ideas about the interaction of soliton with other types of fields like boson or fermion field. Okay, the first time soliton was observed in Edinburgh Canal in Scotland. It was John Scott Russell that first saw it in 1834. So that when a boat stopped in front of it, it created a bump of water that started moving without decay for a long distance, miles and miles. It moved without changing shape and without losing shape. Then he got really curious because he knew that this is, till that moment, no one thought these kind of waves are possible to appear in nature. And there was no theory for that. So actually he spent many years of his life then studying this phenomenon. This is actually this picture in the left is recreation of the event that Russell observed in 1834. Then you can see that many people then tried to recreate it actually in canals that they are almost one-dimensional. These waves are not difficult to create, as you can see even in the other picture in the right. Then in 1844, Russell tried to reproduce it in experiment with wave tank and with the water in creating something one-dimensional and trying to reproduce this phenomenon, and could understand really interesting behavior, could understand the behavior of this kind of solitons. For example, he understood that if you have a big mass of water, you can create two or more solitons that they don't change shape while they are moving. They are like isolated, each of them isolated, like an isolated pulse moving. And so he wrote in his observation in a paper in 1844, but people didn't really pay attention to that because it seemed really strange. It was a phenomenon that was not observed before, and people were not believing that something like this can be created. Then it was Boussinesq and Rayleigh. In independent works in 1871 and 76, they tried to formulate it. So they thought that these waves can be explained with this second hypersquared shape in this form that I wrote here. So this is actually the waves we see in water. But anyway, it was some guess. because this solution should come from an equation of motion, but it was not coming from any equation of motion. Until the work of Korteweg and De Vries, his student, that they could write an equation that the solution of it is this second hyper squared, where this u is the amplitude of these kind of waves. Okay, the dot shows the derivative in time, and prime shows derivative in space, which is this x is the height of the water, how it changes. Then it is called, after their work, it was called KdV equation, which is really important equation historically and even mathematically. Then now it is known that they are really interesting. They are equation of motion of really interesting waves that they behave like particles. Okay. Then after that, it came the concept of integrable systems, and then how to have nonlinear equations that you can somehow relate them to some linear equations. Okay, some linear behavior, some superposition behavior you see, which is not easy to understand from nonlinear equations. And then people try to connect this with the concept of the symmetries behind it. So if you have many symmetries behind this system, then the actual number of degrees of freedom reduces to the point that you can, everything changes to algebraic equations and integration that you simply, in principle, you can find the solution. It doesn't mean you do, but in principle, it's possible to solve it analytically. Then actually it didn't take people's attention till the work of Zabusky and Kruskal in 1965, which is more than 1 century after, that they did numerical calculation and showed how these waves behave in the collision. Then they started actually the wave with the cosine. And then with this equation of motion, you can see that it breaks to some bumps. And then these bumps, after the collision, although in the collision they behave non-linearly and superposition principle doesn't work, but after that they keep the shape. They are reappearing in the same shape that they had in the beginning. Then from there, it actually attracted many mathematicians and physicists to study these kind of systems, because this is something like Fourier expansion of the wave, although the system is nonlinear. So here you can see the KdV, the solution of the KdV equation. If you have like 2 bumps, and if you look at different times when they are moving, you will see that the ones with higher amplitude, they move faster than the shorter ones. Then you can see that how it's from left to right, you can see that how they collide, and after the collision in the second column, you will see that they reappear the same way they were in the beginning. Okay, if you want, you can look at it in 3-dimensional graph, that you will see 2 waves coming and the same 2 waves leaving, although there can be a phase shift in the middle. If you look, it's not really a continuation of the line. There is a phase shift and then reappears the same type of bumps. Okay, so this is the way people define solitary wave and soliton, although there are some variations in the literature, but this is the most common definition for them. Okay, if you have the waves that they have localized energy density and finite energy, and while they are moving, they keep the shape, you call them solitary waves. So in this case, we are talking about isolated bumps that we saw before. But if they collide and after the collision, they are still with the same shape, except for a phase shift they can have, okay? But it doesn't mean anything. It is recreated after the collision with the same shape. This is a much more, it is much stricter condition to have a soliton. And this is exactly the definition of being, having an integrable system, okay? Because we have nonlinear equations, but after the collision, you will have the same type of solutions that you had in the beginning, okay? Then the examples for this kind of solutions is KdV equation, which is completely integrable. Nonlinear Schrödinger equation is completely integrable. You have sign-Gordon equation. In different contexts, they can be really important equations. For example, in KdV equation, it can be important for the acoustic waves of ions in plasma, or for the these kind of waves that we saw in water or any kind of fluid. Nonlinear Schrödinger equation can be really important in optics to have dark and bright solitons. Sign-Gordon equation actually appears in many different contexts. And phi-4 equation, which is really important, that appears actually in really different contexts, from high energy physics to condensed matter, or QCD. So, but phi-4 is the one that is not integrable. So when it is isolated, it keeps the shape. So it is solitary wave, but it's, rigorously speaking, is not a soliton, because it's not integrable. It means after the collision, it has chaotic behavior. So it doesn't keep the shape after, and actually this is exactly what we are interested in this presentation, that it is much richer after the collision. You can have really different phenomenon, that it is not like integrable system, that it keeps the shape after and it's just a phase shift can happen. So if we want to, this was some historical context and how this entered in the area of physics and mathematics. But now let's look at it more rigorously. For example, the simplest case that you can imagine, it's 1 + 1 dimensional case with, for example, the potential can be phi-4 potential. This is the most known potential. That if you look at the shape of the potential, it has 2 minima. To have a soliton, you need at least 2 minima. So here, these 2 minima, they are called trivial minima because they are not x dependent, but you can show that the solution of the system can be, besides these 2 minima, can have 2 other minima interpolating between them, from left to right or right to left. Then you can see this shape. This is like tangent hyper solution, and tangent hyper, it is exactly connecting these 2 minima. If you have the plus sign is called kink, and the minus sign is called anti-kink, okay? So then if you calculate the energy density and then the total energy, which is called the soliton mass, you will see that this lambda is the coupling, okay? It's that self-coupling. If you work in a weak coupling regime, you will see that the mass of the soliton is related to lambda, but it is related to 1 over lambda. So it means that for weak coupling, soliton is highly massive. So actually, this creates really interesting effect. For example, if you want to consider the interaction of soliton with other types of fields, then you can consider the soliton as classical wave, or even it behaves like a particles. Because of that, it is called soliton. So you will see that you can consider them as classical, and the other fields as quantum mechanical or quantum field objects. Okay, here you can see that the energy density is localized, as you can see here. And then if you calculate the integration of it, you get this m cubed over lambda, which is the mass of the soliton, or the total energy of this system. Okay, but these kind of solutions have higher energy compared to the trivial vacuum, that they are X independent. So what protects this kind of system? In the case of that, in the beginning when I talked about the integrable systems, what protects the system is the number of symmetries behind it. For example, if you have KdV equation, the degrees of freedom, because it's a field, so it has infinite degrees of freedom. But then you can show that for example, for KdV or nonlinear Schrodinger equation, you have infinite infinite symmetries, continuous symmetries behind the system, which makes the system integrable. So what protects the system to keep the same shape is the symmetries behind it and in the integrability of the system. But if you look at one isolated kink, you will see that the energy of this kink is higher than the trivial vacuum. So it should decay to the trivial vacuum, because we know the principle of the minimum energy. But here you can show that the system is topologically protected. So you can see that you can define topological charge for the system that is related to the value of the field at infinities. So because of that, it is called topological, because the detail of the geometry of this soliton or this kink in the middle doesn't matter. What matters is just the value at infinities. So, but this whole thing I wrote here, it's for 1 + 1 dimension. The concept gets a bit more complicated when you go to higher dimensions. But what matters here, when this Q is 0, you have non-topological solitons, so they are not protected with the topology, and they simply decay to the trivial solution. If you want to have a stable soliton which is non-topological, you need to put something there which makes it stable. For example, you could add electric charge there. So then you could guarantee electric charge, it is conserved, so you could guarantee the stability of the system. But if you don't have it, the system has higher energy, so will decay to the trivial solution. But the ones with Q non-zero, they are topological soliton, and the thing behind it, it's related to the homotopy group and homotopy classes, that you can show that there is no continuous map that you can go from one homotopy class to another homotopy class. It costs infinite energy in physical context, so it won't happen, okay? So, which means that the system is protected against decay because of the topology of these kind of solitons. Okay. Then there is another thing important for the stability, which is the BPS or self-duality condition. The BPS condition is, if you have the Euler-Lagrange equation is second order in general. So if you can reduce it to first order and then solve it, this is, we say that it is satisfying the BPS condition, okay, which is always valid for 1 + 1 dimension solitons. Then you can do, here you can relate it to this W, which is called superpotential, which comes from the supersymmetry context. So if you look at the energy of the system, and if you do some playing with this energy density, like if you do the squaring here, you will see that what is remains out, it is exactly related to that topological charge that we defined. Okay, so this value, the first part is squared, so it is always non-negative. So the minimum of this can be 0, which means that the minimum energy here is that value Q, which is the topological charge of the system. And so if it is the minimum energy, so if the system saturates BPS condition, then the energy will be minimum, so it will be stable. So up to here, we introduced 3 different concepts for the stability of the soliton and then soliton collisions, which was the integrability that was protecting against the collision, the topology of the system, which was protecting isolated solitons, and besides that, this BPS condition, if it is saturated, the energy is minimum, so the system is stable. Okay, so then you can see that, okay, what's the point? We are working with 1 + 1 dimensions, so nothing in nature is 1 + 1. The nature we know it's 3 + 1 dimensions. But the point is, if you have enough symmetry in the system, in practice, the system you study can be in lower dimension. You can reduce it to lower dimension. For example, if you have a polymer called polyacetylene, it has chain of atoms, okay? Then it has these layers of this chain of atoms that electron can move in each layer, but can't hop to a different layer, okay? So in practice, the system is one-dimensional. And then the interesting part about polyacetylene is that the system, imagine, normally there is nothing in nature that stays still. Everything moves. So because of the zero point motion, or because of temperature, the excitation. So, but in this specific polymer, instead of having oscillations around each atom site, the atoms move a bit to the right or a bit to the left and then oscillate around this new point, okay? That we showed it here with this A and B, okay? And the system has parity symmetry, so it doesn't matter. It goes first to the left and then oscillates, or goes to the right and then oscillates. So, so it means that it does it arbitrarily. But the interesting point is, in the domains that, imagine in one domain you have this type A motion, like going to the right, for example, and type B going to the left and then oscillating. The wall between these two regions, it creates something like a defect. It's kind of mismatching. Then this is exactly where the kink appears if you introduce a field or displacement field, which is the phonon field here. And then this phonon field is x dependent, okay? And then you can see that you will have something like this tangent hyper behavior, which is going from one trivial vacuum to another, which is going from like configuration A to configuration B, or the other way around. And then you can associate a potential something like phi-4 potential. So then you can see that in practice, the system has the behavior, has the potential of phi-4, and then it has these kink defects, or if you like, because it can be in higher dimension, then in higher dimension, the kink changes to domain wall. So you will have this domain wall configuration for the displacement. Okay, so this is one example. Then, okay, as I said, in higher dimension, the kink is called domain wall, that can have really different types that I showed, the 4 types that can exist. Then imagine if you have, for example, you have in the magnetic material, you have like some regions, you have like spin up, another region you have spin down, and the wall between these up and down creates kind of domain wall because it's connecting one vacuum to another, okay? So it's kind of kink in higher dimension. Then the same kind of objects can appear in optics, for example, with bright and dark solitons. The bright soliton is what you see on top, and the dark soliton what you see below. Actually, the dark soliton is lack of light. Okay, this is the intensity. Okay, you're seeing. And then if it has a bump in the center, it is bright, and it has, if it is minimum at the center, is dark, and the dark one is topological, so it's more stable. But on the other hand, it means lack of light, so it's much more complicated to produce them in experiments. Okay, then there are other types in higher dimensions that they are different. For example, vortex can appear in the context of superconductivity and superfluidity, and cosmic string in cosmological context. For example, we know that the universe in the beginning was really hot and then underwent a series of symmetry breaking. Then because of these phase transitions appeared a lot of mismatching that or these topological objects that we are searching for them nowadays to see if still we can detect them, okay? One of them is cosmic string, one of the hopeful ones. Then it can appear in different contexts, these kind of topological objects like dislocation and disclination in crystals and liquid crystals, or for example, magnetic monopoles or skyrmions, instantons. I'm not going through these details because they are not really related to what I'm going to explain about our work. Okay, just to have some notion that there can appear in really different dimensions and really different configurations. Just to have some idea. Okay, now this is one of the works we did that I did with my PhD student João, which is the kink excitations and kink anti-kink collisions, looking at the normal and quasi-normal modes and how they affect the behavior of the system. Okay, first, let us understand a bit better what is a normal mode and quasi-normal mode. The normal mode is normal oscillational mode, bound oscillational mode, where the energy and frequency are real. But the this is more familiar to everyone, but quasi-normal modes are more specific because they, besides the oscillation, they can decay while they are oscillating. They are purely outgoing the waves, okay? They follow purely outgoing boundary condition. And because of being outgoing, it means that they leak, which means that the Hamiltonian of the system, because you can look at them classically or quantum mechanically. If you look at them quantum mechanically, it means that this leaking means that the Hamiltonian is not Hermitian, and the system is not normalizable. But they can be really important in many contexts. For example, one of the original works in this, using this kind of modes, was in the explanation of in the explanation for the radioactive materials, which are not completely stable. Gradually the particles tunnel and decay. So this is exactly explained with these quasi-normal modes, because although the barrier here in the potential is large, but gradually the particles can tunnel because this barrier is not infinite. So gradually these particles can decay. And another context that they can be really important, for example, it is in the context of particle physics. In the scattering cross-section, there can appear those peaks, okay? That they are important in this context. And besides that, for example, in merging of the black holes, if you have information about the quasi-normal modes, you can measure the mass of the black holes, okay? So what we are interested in here is these quasi-normal modes in the context of the kink perturbation and in the collision, which is, there are really few works in this line in the literature. So if we imagine, we have the simplest Lagrangian that you can imagine in 1+1 dimension with real scalar field, and the potential, imagine we don't know anything about it. So then we do the small perturbation, we get the linear stability equation with this small perturbation about the King solution. And then we get something, we get a Schrödinger-like equation, just with the difference that energy here is replaced by omega squared, okay? This omega squared plays the role of energy in this Schrödinger-like equation. And let's call this second derivative of the potential as u of x. We call it the linear stability potential. Then this was our idea that let's simplify the system, any type of kinks, okay, that the stability potential of the kink, it's really close to this. Of course, it's not really sharp like a potential well, it's smoothened, but it really captures the main picture here. And then if you change this potential well to have two barriers, and if you consider in this region an excitation, an oscillational mode or shape mode, sometimes it is called vibrational mode, shape mode, or oscillational mode here, okay? The one above the zero mode, because zero mode has just, it encodes the information about the translational symmetry, which means that if you have a kink, then you can move it anywhere you want. It doesn't cost any energy, so it is degenerate in all these positions, okay? So this is just giving the information about the symmetry of the system. But imagine besides this zero mode, we consider one extra vibrational mode here, which is the solution of this Schrödinger equation, Schrödinger-like equation, okay? With this omega squared greater than zero. Then you can see that if you have a bound state in the left picture, okay, then in the right picture, if it is in the region that faces the barrier, the energy will leak and you will have quasi-normal mode. So the bound state changes to scattering state, which decays, okay? So somehow we introduced the concept of normal mode and quasi-normal mode with this really simplified version, okay, of the stability potential. Then, okay, you can write it mathematically in this shape as constant. This lambda and gamma and delta gamma are constant. So we can get back here to this picture. You see that L encodes the information about the potential, this potential well, but what matters most mainly here is the delta L and delta gamma. When the delta gamma goes to zero or delta L goes to infinity, we recover the potential well without the barriers, okay? So we recover our normal mode. So if I play with delta gamma and delta L, I can go gradually from normal mode to quasi-normal mode, or the other way around. Okay, so then to have this linear stability in this shape, the simplest thing we could came up with is the potential to be second order in phi, where the second derivative of it gives a constant, okay, and gives exactly these two potentials that we created, this potential well and potential well with two barriers. The thing we impose here to have well-defined kinks, because the whole point is we want to have a kink and then study the perturbations around this kink with normal and quasi-normal modes. So to have a well-behaved kink, you need to impose the continuity equation. So what we imposed here is continuity equation in the potential and the derivative of the potential, okay? And then we impose the BPS condition for the question of the stability of the system. And then imposing the continuity equation for the potential and derivative of the potential and the BPS condition guarantees the translational symmetry of the system. So there appears always this zero mode. Then one of the typical potentials that we wrote here, you can see that it's actually it is really in a good shape. If you look, it is like the soliton. It looks like the tangent hyper U that you face in 5-4 model. Okay, it's quite similar, and the potential is smooth. Okay, and has 2 minima, so giving the chance for the interpolation between the 2 minima and having a king, as we showed in the right. Okay, so then this system, this is the Schrödinger equation that we know how to solve the system. So for the square well potential, we know the even and odd solutions give these 2 transcendental equations. Okay, for the eigenmodes, for the eigenenergies here. The eigenfunctions, I wrote it here, but it is not important. Just to have some idea how it is the shape. We worked with the even eigenfunctions, but then you could work with the odd ones. You won't lose any generality here. Okay, so then if you now let's look at the potential well with 2 barriers. Then with 2 barriers, what we are interested in is the region that it can leak. Okay, so to have a vibrational mode in the potential well, and now here to turn to quasi-normal mode, which is a scattering mode. So for the scattering, we know how to solve the system for this a potential well with 2 barriers. It's a simple calculation, lengthy simple calculation actually. So then you can find the transmission and reflection coefficients analytically. This is the beauty of this model, because we built everything analytically, which is there is no paper in this line in the literature that you can do the work with normal mode and quasi-normal mode analytically. Everything is numerical, and there are a lot of problems when you do it numerically, because actually to distinguish between the quasi-normal mode, it's really difficult task, and the error exponentially diverges. So if you can solve the system analytically, you gain a much better intuition here, and it's much more trustable, the result of the system, obviously, because it's analytical. So so this transmission and reflection, we showed them in these graphs. Okay, as we know, for the quasi-normal mode, we should be able to see resonance in the transmission coefficient. This is a known fact. Okay, so the point here is we are changing the controlling the parameters of the system to study where these kind of resonances can appear. Okay, so if you look from below to top, is just changing the size of the potential well, so it's not that important. It was just to get some notion how it changes. But from right to left, delta gamma, which is encoding the information about the size of the barrier, the height of the barrier. Okay, when you increase it, you see it gets more and more localized around the gray line here is the oscillational frequency of this quasi-normal mode. So you see that as delta gamma increases, it gets more and it gets narrower around this oscillational frequency. So it means that it is needed a much more fine-tuned frequency to have this resonance, okay, to excite the system actually. Okay, for delta gamma small, still the system, the mode we considered, it couldn't leak because it's below the barrier, so it can't leak. So there is no quasi-normal mode because of that. The gray line here is the normal mode, okay? And when you increase delta gamma, the thing that the difficulty we had here was that delta L and delta gamma, they are encoding the information about the barrier. As I said, delta gamma, the height of the barrier, when it is increasing, when it is decreasing, or the width, when it is increasing, you get closer and closer to the potential well. Okay, so you get closer and closer to the normal mode from quasi-normal mode that you had. But you can see in this figure that when we impose the continuity equations and the BPS condition, the number of the degrees of freedom in the system for the potential well is just 1. What remains when we do this, besides this continuity equation and BPS condition, you need to rescale the parameters, okay? Then it remains just 1 degree of freedom for the potential well and 3 of them for the potential well with 2 barriers, okay? So in this case, you will see that the delta L and delta gamma, they are not independent when you fix gamma and L, okay? So it means that we can't simply, as you see in this figure, we can't simply decrease delta gamma or increase delta L to get closer and closer to the potential well. But there is one interesting point that from even you can see it from the slope here. For small delta gamma, the delta gamma effect is more dominant compared to delta L, but for large delta gamma, delta L effect is dominant. Okay, so now let's get back to this to these figures. So when I increase the delta gamma, it means delta L effect is dominant, so delta L is increasing. When delta L is increasing, you're getting closer and closer to the potential well, potential well that you had, which means that you are going from quasi-normal mode to a normal mode. You are getting closer to this transition, which means that it should be really fine-tuned, because for the normal mode, it's exactly that frequency. So you need more fine-tuned frequency here for the resonance to appear. Okay, so besides that, we looked at the decay rates and the oscillational frequency of the quasi-normal modes. Okay, as I said, the quasi-normal modes are purely outgoing, following purely outgoing boundary condition, okay, which means that in the scattering wave function that we saw here, F1 should be 0 because it's purely outgoing, okay, and when you impose F1 equals 0, you can solve, you can see that you will get this equation to solve, okay. When you separate the real part and the imaginary part, you can solve for the oscillational frequency here, the capital omega, and the decay rate gamma, okay. Then you can see that for small delta gamma, which is the dominant effect is delta gamma effect, still there didn't appear the quasi-normal mode, because still the system couldn't decay because the mode is below the barrier, okay, so can't tunnel. So up to specific delta gamma, there is no leak, okay, as expected. Then as soon as you pass that barrier, starts leaking, so delta gamma increases. But to explain why again it decreases, you should remember that delta gamma, when the delta gamma is large, then for large delta gamma, the effect of delta L is more dominant, which means that we are getting closer and closer to potential well, which is in the potential well, there is no decay. So it's getting closer and closer to that limit, okay? Then you can look at also the frequency here, the oscillational frequency. At first, it is close to, for small delta gamma, we are close to the potential well, so the frequency starts from the normal mode, really close to that normal mode. Then it reduces because the potential is reducing. Then in this dotted line, we showed that the transition from the normal mode to quasi-normal mode, because after a specific height of the barrier, you will have the quasi-normal modes start leaking, okay? But then when you increase delta gamma, gradually the effect of delta L will be more dominant, so you will get closer again to the potential well. So in this case, you will see that the frequency is getting close to those to the normal modes of that potential well you're considering.